Hey everyone, welcome back to the lab. In this video, we're going to be talking about types versus no types, how types allow code to scale across developers, organizations, and lines of code, or otherwise like code base size, volume of logic, however you want to think about that. And so static versus dynamic typing is one of the many evergreen arguments in the software engineering community. You got like the Python and Ruby and Elixir and Clojure folks on the dynamic side, and on the static side, you've got more like the C Sharps, the Javas, now kind of Rust, F Sharp, Go to a lesser extent. Don't love their types, but that's the kind of general dichotomy we've got going on. And now in this post, I am not going to argue static versus dynamic. I think they both have their pros and cons, and largely this is, I think, a false dichotomy that kind of pits people against each other based on like the language they're familiar with and that they like. So I don't know if it's that productive. Also, I think that the reason static versus dynamic hurts is like there's actually like a whole matrix of what typing is and can be, from like strict typing to loose typing, from static typing to inferred typing, that really kind of changes your approach to using the types. And I think a lot of people's views on programming as kind of vibes of like how they've used it in the past. And so I think, the static versus dynamic dichotomy maybe is not the most useful perspective on this. And so instead what I'm doing from this post is trying to illustrate kind of like the differences between typed and non-typed logic flows without taking into account like the implementations of these things, because you can implement things in a lot of ways, to kind of highlight how these approaches scale across organizations and code bases, and really like use cases that you find yourself in commonly when you're building software. And so, yeah, that's what we're going to do in this post. Okay, so first, I want to start off with what are types? And essentially, types are labels on code flows. Obviously, reality is like a lot more nuanced than this, but we can basically simplify it to this. And they'd say what kind of values pass through this code flow. And this is useful because if you know what kind of value is in a flow, then you can have a better idea of what it represents and how you might and might not want to use that to accomplish whatever your goals are. Now, I often like to think of code flows like wires and types as adding color codes to the wire. It doesn't change the wire itself, like what's going through it. It just makes it easier to spot what is in the wire and thus intuit what its purpose and usefulness is. Now, I go into this metaphor of like logic flows as wires way deeper in this much longer essay, why type-safe programming languages are better than dynamic and lead to faster, safer software at scale. So you might consider looking at that if you want more information on the metaphor. And so that's essentially my thesis here, is that, here's a little diagram I made. I'm playing around with more like vector graphics and stuff of like types versus no types. And so if we think of these code flows as wires, no types is like we got all the wires, but they kind of all look the same, and like, we can untangle them. You just got to trace this, but like sometimes it's confusing. It's like, oh, which wire is this now? They crossed over. What's going on? So you really got to kind of do a little manual trace of this if things go wrong, to rewire it, change it, whatever. And then types are just like, it's the yellow wire, it's the red wire, the blue wire, like, so it's just makes it a little bit easier to kind of see what's going on in the wires, and thus easier to see what's going on in the logic flows. And that's basically it. So in the rest of this post, we're going to go into like more details and examples about this to try and explain why I think this is true. Okay, so why are types useful? So types are useful for code flows for the same reason that labels, or really wire management in general, is useful for wire. They help you figure out what a wire does and intuit what it's used for, which is necessary context if you're going to change the wiring. And when you just have like a few things to wire, like your personal desk, like my desk set up here, it doesn't really matter if you have good labeling or wire management on your system. Like you can probably figure it out by just doing the tracing that I was showing you earlier, like, my monitor's not working, Is it the HDMI cable? Like, you just find the HDMI cable and you trace it under your desk by pulling on it, and like, you can figure it out. It's like annoying, but like you can do it. But once you get up to like hundreds of wires, which is like, a data center rack where they got like all the little servers in the rack and stuff, it starts to become a burden to figure out what each wire does just to rewire something. And if that's like your whole job is to do the rewiring, you kind of want to make it easier on yourself, because that's like an annoying job to trace the thing, and deal with the hundreds of wires. And the truth is that like software engineering really is all about wiring and rewiring code flows, logic flows. And so this idea of making wiring and rewiring easier is actually directly applicable to building software faster and safer, in my opinion, because I think most 90% of what we do is just plumbing, CRUD logic flows and stuff. And so if you make that part easier, everything else kind of gets easier, so you can focus on the actual hard parts, like the algorithm, inside your system, not the dumb wiring part. And now there are many ways to manage wires, and so I wanted to go over like a few common ones, and we're going to start off from like kind of the perspective of like wiring in the physical world, and then we'll later go on into like what is the software equivalent of this, and so we can see kind of like, how do we do things right in the real world? How are we doing things today in software, and hopefully back our ways into like maybe what you should actually be doing in software to like learn from what we're doing in the real world with wiring. The first thing we'll do is like no labels, no management. This is like dynamic types. There's like poor code structure. This is probably like your cousin or sibling or someone who's learning to code. They're writing their first programs. This is probably what they're doing. And basically you just like plug stuff in and leave the wires hanging. This is, probably what you did for your personal desk when you were younger. This works for these small systems, but it is a bit of a pain to rewire when you need to like change out the monitor or change out the HDMI for a VGA or something like that, because you have to trace the wiring by looking at the ends. If it's the monitor I got to change, I got to start down there, then I got to trace it all the way down by pulling on it, figure out which one goes into the power cord or wherever it's going, and then kind of like unplug it. And then if you don't have good wire management, then it's probably a mess of wires down there, so you got to unknot the thing without unplugging anything else. So it's just a bit of a mess, and it's just like very tedious. But like on a personal scale, when you're not changing out your desk that much, like it's fine. Once every few months maybe you got to do the rewiring, and so you incur the cost then. And like this is probably what the back of your parents' entertainment system looks like, unless you took the time to do it yourself. It's probably just like a mess back there of cords and wires and HDMIs going everywhere, and it's kind of annoying. So you probably start there, and then eventually you go into like no labels, but you have some management, and this is more like dynamic types and decent code structure. And so this is when you just kind of plug stuff in, but then like now you're starting to wrap the cords up, right? Like you're pulling in the slack, you're wrapping them up with these little like Velcro things, so that all the wires are like together. And so when you need to change something out, you still need to trace the wires from the ends and pull on stuff to make sure that this is the wire you're actually looking at. But unwinding it is usually easier because like there's no knots, right? It's like once you find the right wire, it's all together. You just unplug it. You can let out the slack. You can put the slack together. And this is probably what your personal workspace desk wiring looks like today. Like you've probably gone through a few workspaces. Now that you're on like your third, fourth workspace, you kind of know that like wiring like this makes it a little easier, even if it takes a little bit longer to set up. And so that's probably what you're using today. And this is like, you got some decent code structure, but you're still using dynamic types. And so you've got maybe utils folder, models, stuff like that. A little bit easier to look around and unwind stuff. Then we might go further. We might have like one sticky note label on the ends. And this is more like dynamic types with some value assertions thrown in there. And this makes it easier to see what a label is so that you can quickly change it out at each end. So this might be like, your house's fuse box. It usually has labels there of like saying what each fuse is for, like kitchen, living room, whatever. Maybe if it's on your desk and you have a bunch of power cords, you might have some labels near where the power is to say like, oh, this is monitor 2. This is like my Xbox, this is my computer, something like that. So we have values at the end so we kind of know what they control, so we can kind of like zip over there and change it out, which is helpful for that part of it. And for like small desks, it doesn't really matter. But when you get to these like larger systems where we can't necessarily trace very easily, sometimes it gets confusing in the middle. And so, for example, if you had to open your wall for like the fuses or something and the wires weren't wired, you'd be like, well, which one is this? Even though you had the things on the ends, you don't necessarily know what it is in the middle. And so unwinding that can be a little hard because really you have to do the full trace just to figure out what that wire is. And then the next version up is like sticky notes labels at regular intervals. So this is dynamic types with value asserts and probably good naming in the middle. And so it's basically that idea of like we have labels on the ends, but now at regular intervals, we're putting like what is in this. And so now we don't have that problem of like, oh, I'm trying to change this chord out. Like, is this wire important? Is this the wire I was looking for? So it kind of helps you from not needing to do the full trace. And this is probably more common in like really like plumbing, I would say, is probably the best real world version we have of this, like city plumbing, plumbing in your building. If you're in an apartment building, like you see those pipes everywhere, and they'll usually on like regular intervals have like, this is pipe G or something. And so that way, you know, they know how to turn it off at the source, but they can also trace where the plumbing is and be like, oh, I know what pipe this is, kind of wherever they see a leak or something like that. So it saves you on that full tracing lookup when you need to do work in the middle. And honestly, software engineering a lot is that plumbing in the middle. And then finally, we get to color-coded wires. So each wire is unique by look. You don't have to find the nearest interval. The whole thing says exactly what it is. And this is more like types in software. So it's the same as the above, but we don't need to like manage these labels. It's really baked into the wire. So we can look at the ends, we know it's there. We can look at anywhere in the middle, we know what it is. And this is probably more similar to what your data center's cabling looks like. Now, granted, in the real world, we don't really have like infinite colors of cables. And so more often what you'll see is color-coded cables for the type of cable it is, which I guess is similar to like coding, but in coding with types, you can imagine we can have like infinite number of types and each of them are easily differentiable. But generally, this is kind of what you see in data centers, right? Like the Ethernets will have different colors, power will have different colors, they might have different colors to different racks. Stuff like that. It's a visual of like, what is this thing, which makes it very easy to see at any point what's in it, and also to see if maybe the wrong thing is wrong. Like, why is the green wire with the pink wires? That seems wrong. Maybe we should take a look at that. And so all of these management techniques aim to accomplish the same thing. They make it easier to manage and change our system by adding visibility into what each wire is and does so we can avoid breaking it by accident. We're basically acknowledging that wire management can get a bit tedious. It's easy to make mistakes here, and so we are using techniques to try and avoid these common pitfalls. Okay, so that's trying to make like the real world analogies of what these techniques are. Now we're going to talk about types for no types for software at scale and trying to kind of bridge that gap between what's happening in the real world and the problems we face to show kind of how that aligns with what's happening in software and what we can learn from that. And so now let's think about our labeling systems work for wiring at scale. If we think about what large engineering teams do, it's basically just a bunch of code flow plumbing on a large code base. And what this means is there's tons of different wires going every which way, crisscrossing, coming from different places, owned by different teams. There's going to be hundreds of changes to these wirings going out every day. So the wiring isn't static. It's not like your house where you can like, you know, like, oh, I checked that 5 years ago and I put the label on it and it's still right. No, it changed, you know, hundreds of times since the last time you looked at it. And it's also very unlikely that any one engineer understands the full wiring layout. And I think this is an often overlooked thing. People are like, oh, they're senior engineer. They've been here for like 2 years and stuff. But it's like the thing that they built a year ago, it's not that same thing anymore because we've added so many changes. We've changed how the system works. We've changed where the origins come in and stuff. So even if they knew the full system last year, the system has likely changed so much that their understanding and mental model of that system that they created is now stale. It is not true anymore. And I think this is critical to avoid these kinds of things where it's like, I assume I know what this is because I did know what it was at one time and I was correct. But the system may not be that way anymore. And so we got to protect against that. And so really what this means is that we've got a wire management problem at scale, right? We got a bunch of maintainers. No one knows what all the wires do. And we're doing hundreds of changes to the wiring every day. So even if you did know what they do, it's not going to be the same thing today as it was yesterday. And so now let's see how our wire management solutions stack up to these problems. Now, first, I want to touch on some strategies we generally want to avoid. This is going to be like no labels, no management, which is dynamic types and poor code structure. This is just bad code. Don't do it. You know, it might work for your personal desk, but you certainly don't want to bank your company on this kind of thing scaling, because it just like won't scale. The next one is like no labels but some management. This is like dynamic types and decent code structure. I think this is okay for small teams and code bases, startups, side projects, stuff like that. However, as soon as you start to try and scale to like new devs on the team, or your code base starts growing to be pretty large, it's going to be pretty apparent how non-obvious these wires are. Like how every house has like that light switch and there's like tape on it that's like, do not turn off. And it's like, why not? It's like not apparent, but it's like, because over the years you found that this thing is broken. When you start to add new devs, they don't have that tribal knowledge. And so it's going to be very clear like how you might understand the wire management thing, but it doesn't really work because nobody else does. And that's the whole point, is that other people have to figure it out. And you'll see this because there's just going to be a large frequency of mistakes that you think are obvious mistakes, but is unclear to anyone else, leading to breakages. And so it's going to slow you down. So those are things we probably want to avoid. They're pretty clear, self-explanatory, why like, they do work, but probably don't do them on teams or for like, code that your business runs on, or like won't work at like super large scale of code bases. And so I want to skip those and kind of focus on those that like I think are more common practice in the industry. These are kind of the more acceptable approaches that we take, and kind of look at the pros and cons of these. And so the one sticky note label on the end. So, we've got our cord, and it's like, oh, this is the monitor cord and the part that's attached to the monitor. And then we got, this is the monitor cord, maybe at like its connection to my electricity, or maybe it's connection to the HDMI and in the back of my computer, so I know like which one it goes to. This one is pretty common, and this is basically the same as like dynamic types with value asserts. Most often with value asserts near the ends on the critical parts of it, so something coming into your system and then before you like write to a database or do something important with it. And I'm saying this as a distinction because there's many ways to do value asserts, which we'll go into later. But this is the one where like you have it only at the ends, right? So input, output kind of thing at the end of your flow. And I think this can work for a while. You basically have asserts at the end of the flows, which gives you confidence that at least the stuff in the middle isn't breaking everything. I would also argue that this is probably more like testing in dynamic languages, because you are writing stuff. And so really you're kind of asserting the inputs, outputs kind of at the end of the flow, but maybe not as good a fit of the metaphor. But what this means is that, during development, devs will often end up breaking stuff in the middle on accident and won't know about it until test time, because a lot of the plumbing we do is kind of in the middle. It's like change this thing to only do this thing when this thing happens. And we don't actually know whether the value going through works or not until we run the flow. Because in the middle, everything can look correct, but you might have broken things on the end and you won't know. And then it's going to take a long time to fix this, right? Because you're like, okay, well, what I did over here I thought was right, but now it's breaking this thing on the outside. So now I got to kind of trace through and figure out like, where did the values come from? What is it supposed to do? And where did I mess that up? And this tracing can be really tedious and time consuming depending on how convoluted the wire is. Like, when you're tracing these like A to B wires, it's not going to be like your desk. It's going to be like it's in the full building. And so you're like, well, dang, I know it started out correct in the basement, but now on the 17th floor, I know that whatever I did on floor 10 broke stuff. I got to figure out where this went wrong. And so you got to kind of trace from the basement up to figure out like, where is this not working anymore, And so like, you can do this, obviously people do this in their jobs, but it's just kind of time consuming, And I think the other part of this is because we only know this like after the fact, we only have the value assert when we've actually tested through this code and only at the ends. It's possible that we break something, we fix it, but then the wire will change out from under us as we're working. And so this is very common in larger teams, hundreds of changes being made every day. That thing that you checked on Tuesday may not be the same as it was on Thursday. And so you could make it all work on your branch, and then you try to like, test it on master, and now all of a sudden you got another breakage and you got to do that whole thing again. And so it's like you do all this tedious work, and like, pretty frequently it's all for naught, because that information that you thought was correct is like no longer correct, which just kind of sucks. So that's that side. It works. Teams do this. But it leaves a lot of room for error and rework in the middle, which I personally think is like pretty easy to avoid. So how can we avoid this? Well, the way that you can avoid this in these larger buildings like plumbing and stuff is to have sticky note labels at regular intervals. And so these are the dynamic types of value asserts and good naming kind of at regular intervals. And this one is pretty good because you can often save on the tracing time. You just kind of check the nearest label and you have a good idea of what's in there. You check like the name of the variable, you check what the assertion is asserting, and you can generally have a decent idea that that's correct. That's what's in the wire. Now, unfortunately, a good idea is not the same as knowing for sure. Even though this variable has a nice name and our system isn't broken because the value asserts on each side, on each end are good, there's very little enforcing that this intermediate type is what it says it is. And this is a common source of bugs. You think it's a string, but actually it's a null. It also a common source of confusion. Variable names, just like source code comments, can easily become stale, leading to future devs thinking it's load bearing when perhaps it's been out of date for several months. And so it's like, when you does initially wire a system, maybe they go through and they label all these things. But what are the odds that, the 100 changes since that dev has also changed all the labels and the source code comments and all of the asserts? Now, obviously the asserts are probably correct because if they are wrong, they would have been changed. But are they asserting the right thing? Are we just saying like assert value is not none in Python or assert value is not null? And it's like, okay, we're asserting that there's something here, but what is in there, right? And so we kind of always fall back to these like code names and code comments, but like it's just very unlikely that every change a dev has made, they've traced it forward and back to update those comments. And so now our information is stale. And so even though we have these asserts at every level, we're kind of like back to square one where if like something's broken in the middle, we still got to trace forward and backwards to feel like, what was this supposed to be? And so yeah, it incurs this full trace cost, even though we've added this extra information, because at the end of the day, we only know that we've broken, A to B. In the middle, we might have some asserts, some naming, but because it's not actually load bearing, it's not enforcing what's in the wire, we don't know where the breakage is. And so we still got to do the full trace to figure it out. And now a fix to this is to use good naming, obviously, but again, that'll probably be stale, but also to at regular intervals use value asserts. And I think this is pretty common, but often not implemented well. So we might do value asserts on like a property or like make sure that something's null. But really, if you're doing this, you almost need to do more of like Azad for TypeScript or like Pydantic for Python, where it's not just asserting that, these sanity checks, it's really asserting what every property is and stuff on it, because we need to have a checkpoint to know like, did it break here or not? And so what this unlocks is like bisecting for an issue. We don't have to do a full trace. We can be like, well, is it still the thing that I expect here? Is it still the thing that I expect here? And you can get that automatically because the code itself is checking it. And this does incur extra runtime costs, but largely performance is not the biggest bottleneck. Usually it's like dev cost. And so I think it's usually worth it. And so I think this is a pretty reasonable solution. This is what you'll see at a lot of companies. This is basically what we did in Python at Instagram. This is what we do in Python at Rippling, is we don't have a type system with these dynamic languages, so we try and do runtime asserts to try and get and approach what you can get with types, to get that early signal that like, hey, this value isn't what you think it is. You need to look at this. And so I think this works. It can be good. Now, the problem with this is that you only find out if you did the wiring incorrectly if you try the wire itself. And this is kind of like electrical wiring IRL. Like, we can wire what looks correct on the surface, like the plugs will go into on each end, but we don't actually know if it's going to work until we flip the switch to see if the light actually comes on. And so you see this frequently, like you're testing USB cables, or like you're like, why isn't this thing on? And you check the power cord, and like at the end of the day, that's what you need to do. You need to test the thing, but it's like you don't get any early signal. And so often it can be a little bit frustrating to be like, okay, I plugged in the things, let's go to the fuse box and see if it's working. And like it doesn't work, and I got to go back and try everything again. It's kind of annoying. And so I'm gonna say that this works. It's like a viable solution. A lot of teams do this. This is the closest you're gonna get to like what types provide you in dynamic languages like Python, Ruby, Elixir, stuff like that. But we do incur the cost of not knowing if the wiring works until we explicitly test it. And generally this means longer cycle times and a bit more rework as we go back and forth from the change to the test. Simply because we can't know when we're wiring if it's like should work or not. We're kind of just like guessing like this works based on the information we have. And so what this means is that like if you're not testing 100% of your wires, like, all the code flows, it's very easy for a bad wire connection to go unnoticed until you need it and find out that the thing is broken. And I'm not saying types don't do this. Like it's of course possible to plumb your types and get them wrong, but I'm saying there's some versions of things that can slip through in this form of type checking, which is like we put them together, we don't get any signal, but these are the wrong types. These don't match up, but we don't know until we actually test the full code path. Okay, so now let's go on to color-coded wires so that each wire is unique by look, which is essentially types, right? And this one's interesting because it combines a lot of the benefits of the approaches above it. We get fast lookups for what's in the wires because we have labels. And crucially, these labels are like up to date, right? Like we don't have like bad naming throughout, or even if you do have bad naming throughout, you see the wire, you can check exactly what that color means, what is in the wire. It's also easy to spot inconsistencies and connections, right? So similar to like value asserts where you're trying at regular intervals to check what's in this to make sure that it is what it is, we can pretty easily see that like, well, we have this value assert, we thought it was, red, but actually it's green. And then what this unlocks is automatic error checking, right? We can know before we even run this, we don't have to run down to the basement and flip the fuse box and see if like the light turns on, although you should still do that. We can be like, well, we got a yellow wire and a blue wire connecting. That's probably not going to work, okay? Like you can't just put a red and a green wire together. Like we need a converter, all right? And so it's kind of like accomplishing all of what we've tried to accomplish with the other approaches, but with just less work. We don't have to keep all the labels up to date. When something's broken, we often don't have to do a full trace of things. We can basically just look at the wires and be like, well, are the colors right? Do the colors match up? And if not, we have a pretty good idea of like where we need to bisect to. Now to be clear that like this doesn't remove the need to test. You still need to, flip the switch, make sure the lights come on at the end of the day, because that's why you wrote the system in the first place. And you still need to structure your code well, right? Like even if we have these colored wires, if it's all tied in knots, then our job of plumbing is going to be like hard and tedious and like, that sucks. But it does make it a bit easier to manage because it removes several classes of common errors that we get from the other approaches, and it doesn't really take more time or effort or anything like that. And so I'm not saying you can't write good software without types. There's plenty of teams that do this, and it's like brilliant work, and it's like very cool to see. But I am saying that types are a simple tool for avoiding very common pitfalls in software engineering. Things like wiring things incorrectly, and then fixing them faster when the errors do occur, because they will occur. So the blue wire to the blue wire, the yellow wire to the yellow wire, and if it's a red to a green, maybe we got to double check that and make sure we're doing that conversion correctly. Now there are other ways to accomplish the same things, but I think types are the best simple scalable system that I've found to do so to solve these particular pitfalls. Now for a more in-depth exploration of types versus no types and the code flows as wires metaphor, you can check out my full essay, Why Type-Safe Programming Languages Are Better Than Dynamic and Lead to Faster, Safer Software at Scale. This video itself actually got much longer than I was expecting given the length of this blog post. But this one does dive into a lot more different examples. And so if you're looking for that, this is probably a good one to look at. Now, if you like this post, you might also like how to write simple tests that scale with code bases, organizations, and changing requirements. You might also be interested in 3 areas I'm exploring to build more side projects faster and cheaper in 2024, or 5 reasons F# is a great Python alternative for scripting, side projects, and enterprise applications. That's it for this video. Thanks for watching, and I'll see you in the next one.